When we look at data, we often see differences between groups, like men are taller than women, and we see relationships between variables like taller people weigh more than shorter people. And the big question will then be, are those differences and those relationships, are they real or not? In order to explain what real is, we are going to look at a very simple data set. And by looking at various combinations of variables and variable types, we can identify very specific differences between groups. If you look at this slide there on the left-hand side, you can see that we can highlight specific differences between groups by using bar charts, and it's also very popular using tables in which you basically highlight the differences. And then on the right-hand side, it's all about relationships, ratios, specific relationships between variables. And there you can see we can use different charts, or we can use box plots or correlations. So let's imagine that we got a research question about the height and the weight of people living in New Zealand. People, then it's logic, it's not practical. We cannot measure the whole population of New Zealand. So it is just logic that an easy way is to just take a random sample and measure the height and the weight of that sample. On top of the height and the weight, we can also collect some additional information, say for example about the gender and the age group of each of the people in our sample. We can then arrange this data in a spreadsheet or a data set. We talk about the data set with the various attributes in columns, where the columns are called variables. So there you will see the columns. I've just follow the yellow arrow and you will see the columns. In other words, the columns are from top to bottom, and that's representing your variables. And the variables will be the object of our inquiry. Most data sets that you are going to work with will contain two types of variables. We've already done it. It's categorical and numerical variables. Categorical variables like gender contains categories as the name suggests, and we think of them as groups or buckets within which the data can be arranged. It is actually quite easy because numeric variables like height, basically you can hear in the name, just like the name suggests, it's numbers. And remember, I told you the golden rule is the moment that you can arrange it on a number line, you must know it's numeric variables. So there we are. We've done it several times, but as you can see, there's our numeric variables on the right-hand side because you can plot it on a number line, and then the categorical variables. And the moment that you work with categorical variables, I told you, you should think about it as buckets. To better understand the data, we can also summarize it and visualize it. In the case of categorical data, we can count up the number of observations in any given category and represent them in a table. There you can see the top green arrow and a bar chart, the bottom green arrow. To summarize numeric data, we are firstly interested in the spread or the distribution of the data. So we might describe the range of the data. There you can see the orange lines on the sides of the number line and the interquartile range. It's basically those purple lines. And we can also include the standard deviation. And to get a sense of the middle of the data, we use the median and the mean. There you can see the green and the red lines in the middle. The mean is probably the most commonly used summary value to represent this kind of data. We can also visualize the data by using a box plot, which is just a visual representation of the range, the interquartile range, and the median. We can also create a histogram to show the shape of the data, like you can see over there, all on the right hand side under the heading numeric. The process of summarizing and visualizing data takes the data from just being numbers and words on a spreadsheet and turns it into something that is meaningful to us, something that we can think about. So before you continue, please stop the recording and say what kind of data yellow and green respectively represent. Of course, your answer is correct. In this simple data set, we have two categorical and two numerical variables. Things become interesting when we look at combinations of variables. For example, one categorical gender, for example, and one numeric variable height, for example. We can group the data by gender. Gender is a categorical variable, as you know, and we can create a summary of the numeric variable, height, that is separated out into those two groups. Just look at the box plots and you will see a blue one for the males and a magenta one for the female. Okay, people, and if you look at the blue circle and the magenta circle there on the right hand side in the table, so just by looking at this summary, we can see that in our sample data that men are on average taller than women, just by looking at the mean. Okay, this was a combination of a categorical and a numerical variable. Of course, there were other possible combinations that we could have looked at, like height and weight, and height and weight are both numerical variables. Just like gender and age are both categorical variables. But remember, people, whenever you look at your data, in each case, we want to see the differences between the groups, or we want to find those correlations between variables. In each of these cases, there are specific statistical tests that we can apply to see if what we are seeing in our sample data has implications for what we think about the wider population. Can we infer anything? In other words, if we look at the sample, whatever we see over here, is it telling us more about the population? Is what we are seeing statistically significant? So people, it's all about different combinations of data. And what I want to do, I want us to look at the 5 most important combinations of data that we have. And we're going to use this simple data set. So we are firstly going to look at what we might observe in our sample data, given that sort of combination of data types. In other words, the combination of data types that you're going to use. And secondly, what statistical test we might apply to determine whether or not we can infer anything about the wider population. We might look at a single categorical variable like gender. Look there on the left-hand side where the yellow arrow is, that column, gender, categorical variable, and it's a single column that we're choosing. And then we're going to use that to do a one sample proportion test. Okay, people, if we've got 2 categorical variables, we will use a chi-square test. So there on the left-hand side, you can see 2 columns. The 2 columns, you already know by this time, it's representing the variables, and it's categorical variables. One categorical variable is gender. The other one is age group. And then if we look to the right-hand side, that's where we see, okay, we've got two categorical variables, and we can use a chi-square test for it. For a single numeric variable, like height, we will do a t-test. Look there on the right-hand side, and there you will also see a box plot. If we have a categorical and a numerical variable, we do either a t-test or analysis of variance, ANOVA, if there are more than two categories in my categorical variable. And people, the last one, if we've got two numeric variables, we simply do a correlation test. Correlation tests are really nice to do. You're going to enjoy it. Long and short of the story, if you look at everything there on the right hand side, and then you can see how data can be divided, even in the table. Really interesting. Data can really tell a story. It is important to see how you can interpret your results. So never take a data set and randomly step around hoping to find something that is statistically significant. So always, before you interrogate the data, start off by defining your question and your hypothesis. So you define your null hypothesis and you decide on an alpha value. And only after the above, you go and you analyze the data. People, if you're going to focus on only one categorical variable, you can probably ask yourself, what can I do with only one categorical variable, like gender, for example? We might ask the question to ourselves, for this research. Is there a difference in the number of men and women in the population? And then we can state it as a hypothesis. We can say, yeah, there is a difference. And people, we can see it just by looking at the data. Say, for example, if you look there on the right-hand side, just by plotting it on a bar chart, you can see, yes, there is a difference. People, in stats, we're going to work with a hypothesis, an alternative hypothesis. In other words, that's usually what we want to prove. We call it the alternative hypothesis. And what we're going to do, we're going to create an opposite statement. In other words, if we want to say in our alternative hypothesis, there is a difference, then the null hypothesis will be there is not a difference. And then we're going to look at the statistics, the probabilities, and at the end of the day, we're either going to reject the null hypothesis or we're going to reject the alternative hypothesis. In other words, if we accept this one will be rejected, or the other way around. It's like a scale that we've got in our hands, and this is what statistics is all about. So just for now, in my own words, just keep this in mind, but I will come back to this and I will explain it in more detail as we go on. So long and short of the story, people, it could have been pure chance that we selected a sample from the population that showed a difference, while there is a possibility that there might be no difference at all. We believe, because even on our bar chart, we can see it looks as if there's a difference. So that's kind of like what we believe. And so that will be our alternative hypothesis, and we're always going to present it with the letters H1, and then the opposite statement will be, no, there's no difference at all, and that will be, the opposite statement will always be our null hypothesis. You must remember that it is just sample data that we work with. So we are definitely not sure whether the population will look exactly like the sample. So the difference that we see might be due to simple chance, like I've said. It might be pure luck, exception, or chance that we selected a sample showing a difference. So this is basically what we're going to say. We believe there is a difference, and we're going to present it with the letters H1. This is our alternative hypothesis. When in actual fact, there is no difference between men and women. In other words, we believe there's a difference, but it might be that there's no difference. And that's going to be our null hypothesis. In other words, if you follow the yellow arrow again, and that's basically what you have to, the opposite statement that you're going to make. In other words, the mutually exclusive statement, because only one of them can be right. If the null hypothesis is true, what are the chances? In other words, what is a probability that we will see the difference that we have observed? In other words, the difference, or even maybe a greater difference for that matter. So we have to look at probability. If we can prove statistically that the probability for the null hypothesis to be true is very low, then we've got like great confidence that it's probably wrong, and then we can reject it. People, before we calculate that probability, the probability, we will call the probability our p-value. In other words, probability value. We must be clear about how small is small enough. Below what value of p would we reject the null hypothesis? We must decide on that cutoff value before we calculate the p-value. And we call that cut-off value, we call it the alpha value. And for the rest of these examples, we will just use an alpha value of 0.05 or 5%. But like I say, the reason why you must decide before the time, if it's really, really a dangerous thing that you're going to do, and you know, hey, the risks are very high, you may be going to choose on choose an alpha value way lower than 5%, maybe 0.01%, you know. But if it's not really important, you know, there's no risk in it, maybe you can even go for a higher p-value. But usually a good p-value is 0.05 or 5%, and we're going to use it for most of our examples. So people, I've been talking about these two mutually exclusive statements. So you will always see that you end up with two possibilities. It's like a scale. And so you always have two scenarios only, like in this case. So in this case, we have the null hypothesis, which is, hey, there's no difference. And then we've got the alternative hypothesis, which is what we believe, that there is a difference. And now, in order to make sure that it was not just coincidence that we've seen what we've seen in the sample, we have to go over and test it statistically. So I believe you can all see this scenario, that we're sitting with two mutually exclusive statements, hypotheses, and the next step will now be to apply a statistical test to see which one we can keep and which one we're supposed to reject. So in this example, because it's one categorical variable only that we're working with, you can go back to slide 27, where I've specifically told you that this will be the test that we will use. So we will use a one sample proportion test, and we will generate a p-value. If the p-value that we're going to generate is less than the alpha, remember the alpha that we chose was 0.05, 5%, then we can reject the null hypothesis and state that the difference that we observed is definitely, it's statistically significant. So then we can say, we are sure there is a difference between, if we look at the weight, a difference in the weight between males and females. So if we decide to not only look at gender, but add another categorical variable, like age, for example, we may have a research question like, does the proportion of males and females differ across age groups? Okay, people, now that we're working with two categorical variables, our hypothesis is that the number of men and women that we observed is dependent on the age category that we look at. In other words, that's our alternative hypothesis. That's what we believe. We believe as people get older, depending on the age groups that they fall in, the relationships between men and women will change. In other words, the proportions change or depend on the age category. And now, after we've stated our hypothesis, we can collect our sample data. And then, when we look at the data, when we analyze it, we can see that proportions do change across the age groups. In other words, in our sample data, proportions are dependent on age category. Okay, so we kind of like think, this is probably supposed to be true for the population as well, but we can't say. In other words, we have to say to ourselves, is that due to chance? So we first have to go and test it again. In order to do our statistic test, we have to formulate a mutually exclusive statement. And this statement will be our null hypothesis. So we're going to test the idea that they are all the same and independent of age category. That's our null hypothesis that we're going to state. So we can conduct a chi-squared test that will give us a p-value. And remember, if the p-value is less than the alpha, then we can reject the null hypothesis and state that our observation that we saw is statistically significant. People, it really is nice when you've got more than one numeric variable to compare them against each other for differences. But you can think for yourself, if we look at just one numeric variable like height, then we do not have any groups to compare for differences. You do not have another numeric variable to look for some sort of relationship. So, what questions can we then ask? It is possible that we can have some kind of theoretical numeric value to compare our data to. For example, in the case of average height, we might have some historic data and wonder if the current population is significantly different from the historic data. So our question might be something like this. Is the average height different from a previously established height? Let us imagine that this previously established height was 1.4 meter, like we've said. So we now want to know if the average height in our current population is different from that 1.4 meter, that historic value. So our hypothesis is that there is a difference. So that's our alternative hypothesis. So it will be H1. But again, we collect some sample data and find that the average height is indeed different from the historic height. So in our sample, we find, yeah, indeed, there is a difference. It's differing from the historic height, but remember, this was only a sample, and we're actually interested in the parameter of the whole population. So we have to ask ourselves, is it statistically significant? So you will see the same process the whole time. People, we believe that there is a difference. H1, our alternative hypothesis. But therefore, we have to formulate a mutually exclusive statement, our null hypothesis. So our null hypothesis would be, there is no difference. Okay, people, you will remember we've looked at our sample, and there in H1, what we've seen in our sample, there is a difference in the sample. That's our alternative hypothesis. And now we formulated the null hypothesis. It's the mutually exclusive statement. In other words, exactly the opposite. We're saying there is no difference. So if there were no difference, like the null hypothesis is saying, in other words, if we find the null hypothesis true, what are the chances? What would be the chances that we can observe the difference that we do observe here in H1, or even a greater difference? In other words, what are the probability? And yeah, of course, if it's going to be, we will take an alpha value of 5%. So if the chances are less than 5%, people, then we can just throw it out and state that, okay, no, what we observe is definitely statistically significant. What we will do next, we will conduct a t-test. And we will compare the averages, and if the p-value is less than the alpha, then we can reject the null hypothesis and state that the observed difference is statistically significant. So our next example will be when we consider both a categorical and a numeric variable at the same time. And then, for example, our question might be something like, is there a difference in the average height of men and women? So based on this question, is there a difference in the height between men and women? People, we found that there is a difference in our observation. And it's also our hypothesis. Our hypothesis is, in other words, what we believe there is a difference. But now we will formulate our null hypothesis because we will assume that there is no difference. By now you will know exactly how it works, but we will conduct a t-test next, and it will give us a p-value, and if that p-value is less than the alpha, we will reject the null and state that the observation is statistically significant. If we have a categorical variable with more than 2 categories, like for example an age group that has 3 categories, look for example at my yellow arrow, and there you will see it age group, and we can distinguish between adult, child and the elderly. So there we can see the 3 categories. Then instead of doing a t-test, we will do an analysis of variance, ANOVA. Okay, people, the good news is that the last combination of variables that we're going to look at in this data set are 2 numeric variables. and we're specifically going to look at height and weight. And in a situation like that, there might be an answer, for example, or a question, for example, like, is there a relationship between height and weight? Our hypothesis is that there is a relationship. So we collect sample data and look at it to confirm. And we see a relationship. But the question is, because remember that relationship that we see is only in the sample, is this real? So people, our first assumption, our null hypothesis, is that there is no correlation between the two variables. In other words, no correlation exists. So if the null hypothesis that there's no relationship, if it were true, if it's not real, what are the chances that we would see the relations that we do see? Here we will conduct a correlation test. A correlation test will give us two things. First, it is going to give you a correlation coefficient, which tells us something about the nature of the association between the two variables. And it will give us a p-value. And again, if the p-value is less than the alpha, we can reject the null hypothesis and state that the correlation that we see is statistically significant. You know that whole procedure by now. And the correlation that we see will be represented by a number that we call the correlation coefficient. So the correlation coefficient is a number between -1 and 1, and it looks at the relationship between two numeric variables. Long and short of the story. As the x variable gets larger and the y variable gets smaller, then we say that they are negatively correlated. So people, here with this two numeric variables, we've been looking at the relationship between height and weight. And just like all the other tests that we did so far, if we get a p-value, look at the green circle there on the number line, and you see that it's smaller than the alpha, which is 5% in this case, then we can reject the null hypothesis, and we can say that what we see is statistically significant. Always remember that the correlation that we see can be represented by a number. And that number, we call that number the correlation coefficient. The correlation coefficient is a number between -1 and 1. And it looks at that relationship between two numeric variables. Here you can see an example. If there is no relationship at all between the variables, then the correlation coefficient will be 0. Look at the magenta circle. Now I want you to concentrate and to look at the red arrow. So just look at the change in the variable on the x-axis. It's represented by the red arrow, the movement of the red arrow, and the influence that it will have in each case on the variable on the y-axis. You will see that as the x variable gets smaller, the y variable gets larger. And then we say that they are negatively correlated. If they are perfectly negatively correlated, then the correlation coefficient will be -1. Look at the magenta circle. All the examples that you've seen so far has been about negative correlations, but basically this was the end of those examples, and The next few slides will show examples of positive correlations. You will see if X goes up, Y goes up as well, then we've got a positive correlation. But if it's like a perfectly positive correlation, then the correlation coefficient will be 1. And just remember that the value of the correlation coefficient can be literally anything between -1 and 1. The very last thing that I want you to take note of is that it doesn't matter which of your variables are on the X and which ones are on the Y axis. The correlation coefficient will be the same.